So yeah, welcome back to the machine learning for 3D data. So from the last lecture, we started to discuss in terms of like how we can calculate some kind of the relationship between the 2D images and the 3D. And based on that, what we are going to do is that basically we are doing some kind of the 3D reconstruction from the multi-view images, and we are going to see some kind of the more some kind of the directed techniques that we can do that for the 3D reconstruction from the images. And for that, we discussed some kind of the basics about the camera model last time, and we are going to move on to the slightly more the kind of the in-depth kind of the things in terms of like how we can do some kind of 3D reconstruction from the images. And then next time, we are also going to move on to the neural rendering, which is also the kind of technique that we are leveraging the neural network for more precise 3D from the images. So just give me a second to set up some Zoom issues here. Okay. Let's see. So last time we basically discussed some kind of bunch of the coordinate system. So basically we are defining some kind of a world coordinate in the 3D space. And depending on where basically the camera is placed, and also the viewing direction of the camera, we are also defining some kind of the camera coordinates, which conversion from the world coordinates to the camera coordinates can be done with some kind of rotation and the translation. And then we also define the image coordinates, which is basically some kind of the output of the projecting things in the 3D space into the 2D image plane. So the conversion from the camera coordinates to the image coordinates is done by some kind of projection, right? So based on that, we are basically discussing two types of the camera parameters. The first one is the intrinsic parameters, which is basically defining some kind of the rotation and the translation from the world coordinate system to the camera coordinate system. So which is not some kind of some intrinsic kind of things about the cameras. It depends on like where we put the camera in this 3D space and also the viewing the direction. The other one is more about the camera, the intrinsic parameters, which is real some kind of literally some kind of intrinsic parameters, which involve some kind of the focal length or some kind of the shifting the image, the plane, right? So it basically also involves some kind of the projection, the process, converting the camera coordinates into the image coordinates. So when you combine these two, this combination like these two is typically called the camera matrix, which is now defined, typically defined with the 3x4 matrix that also maps the world coordinates into the image coordinates, right? So this was kind of the coordinate system we discussed last time, and also the two types of the camera parameters. Like one is the extrinsic parameters, and the other one is the intrinsic parameters. And to basically represent all this kind of the conversion, we also discussed like using the homogeneous coordinate system. So as you can see, the camera matrix is now basically represented with the 3x4 matrix, which means that the 3D point is now represented with the 4-dimensional coordinates, and the coordinates over the image plane is now represented with the 3D coordinates, which is because of the fact that we are using the homogeneous coordinate system, right? So we can see this kind of some relationship across the coordinate system. And especially for the camera, the intrinsic matrix, in the graphics literature, typically we set the Z direction as kind of the viewing direction, the direction of the projection, right? So basically we are basically having the Z-axis in a way that the image plane, the plane where we are projecting things, is basically placed on the plus the region in the 3D space, right? But the thing is that in the pinhole camera system, while we put the image plane in the region where basically the Z becomes the positive, we also need to flip the image, right? Because like the projection wheel becomes the upside down the image, which means that we need to have the flipping at the end. Then it becomes like identical to put the image plane, not the positive reasons, but in the negative reasons, right? So that was like things that we have seen last time. But in the computer vision, the convention, what we can do is that we can basically define the G direction as kind of the viewing direction, not the projection direction. Then it also becomes like identical to put the image plane in the region where the Z becomes the positive, right? So typically what we can see is that some kind of the default camera might be is that we are putting the image plane where the Z becomes 1. Then basically we are having the image plane like this, but we can also control this kind of distance from the origin to the image plane with some kind of some arbitrary number. And this number becomes of the focal length that we also discussed last time. So based on this kind of convention, so it all depends on like how we define the coordinate system and also how we define the image plane in 3D space. When you follow this kind of convention, the first kind of the question is that what would be kind of the camera the intrinsic matrix, the 3x3 matrix, when the focal length is the f and also the shift in the image space is the cx and cy. Can you answer this question? So last time we have seen that in this case, our intrinsic matrix has this form of that, we're having the focal length in the diagonal, we're having the shift term as the translation like this, right? By the way, the question in the Zoom chat was that what's the R and T here? So basically, the camera, the intrinsic matrix involves the two types of the transformation. One is the rotation, and the other one is the translation. So we are having the rotation part here, which is the 3x3 matrix. So R is representing the rotation in the 3D space, and T is the translation also in the 3D space. So this is like 3x3 and 3x1. So the intrinsic matrix becomes the 3x4 matrix, and we are also having another 3x3 matrix, which is the intrinsic matrix. Right? So yeah, so this is the kind of the some typical the intrinsic matrix that we would see for many kind of the some simplistic camera setup. So when we do not assume any kind of the distortion or many other kind of things, typically we're gonna have this kind of the simple some intrinsic matrix, right? Having some focal lengths and the shifting the image plane. So then what if we have some kind of the very special kind of the camera the model like this, which is basically it's kind of the default the camera model where basically the focal length is the 1 and there's a 0 shift in the image space. In this case, we can say that actually it becomes like having the identity matrix as kind of the intrinsic matrix, right? So what can you see is that we can actually consider define some kind of like normalized the 2D coordinates, which is basically the image coordinates when you have the default camera. When you have that the focal length is basically the 1, and also there's no shift in the image space. And you can see that actually this is kind of the some special case when the camera is kind of the default camera, which is also equivalent to projecting all the 3D coordinates to the z=1 plane. Right? So we are basically, when you see that these like the capital X and also the X hat here, these two are basically the homogeneous coordinates, just like having only the extrinsic the parameters of the camera here, and multiplying this without the intrinsic matrix, and basically consider these as kind of the homogeneous coordinates is basically the same. It's like we are projecting all the points in the 3D space into the z=1 plane. Okay, so these three are basically all the identical. So whether we see that whether we have some kind of image coordinates, we did some kind of default camera, the focal length is 1 and there's no shift. It's basically the same that we only have the camera intrinsic matrix here, while basically having the 2D coordinates as kind of the homogeneous coordinates, which is also the same that we are projecting the 3D coordinates into the z=1 plane, right? So we're gonna say that this is kind of the normalized 2D coordinates. So you can see that this is kind of a special case where the camera is kind of some sort of the default camera. And also it's the same that we are just projecting all the things in the 3D space into the z=1 plane. And in terms of the mathematics, the forms, it's the same that we are multiplying only the extrinsic matrix without the intrinsic matrix, because it's the same that intrinsic matrix is basically the identity matrix, while treating the output as kind of homogeneous coordinates, right? Clear? So we're gonna use this term, the normalized 2D coordinates, in the rest of the today's lecture. Any questions on this? And then we also, speaking to the homogeneous coordinates, based on that, we also could discuss the, not the Euclidean, the, Cartesian the space, but the projective, the space. This is kind of especially the case that we can now define some kind of the point at infinity. So the point at infinity could be defined into the finite form, in terms of that we are having the last element in the homogeneous coordinates to be 0, right? So that was the case. And also, by definition of the point at infinity, we could say that there is like only one point at infinity along each of the direction, which means that whether you go to the like one direction or to the other, the opposite direction, you're gonna see the same point at infinity. So two extremes basically meet at the same point, right? And this also means that all the parallel lines also meet at the same point at infinity. So regardless of some kind of offset in the space, like if you are basically heading to the same direction, then you are basically heading to the same point at infinity. So by definition of the point at infinity that we defined last time, and also we could say that there is like also only one line at the infinity, which is basically connecting all the points at infinity, right? So these are like all the things that we also have seen last time. And based on our definition of the point at infinity and also the line at infinity, what we could say is that we can basically have some kind of the very, some kind of general, some kind of the statement like this in terms of that all the two distinct lines are basically intersecting at the one unique point. So including all the line at infinity, there should be some kind of only one intersection point. So even the two parallel lines are basically meeting at the one point, which will become the point at infinity, right? And also for the point as well, if we have some kind of two distinct points, whether the points are the infinity or not, we can also determine like one unique line. So this was also kind of a statement that we could see with the definition of the point at infinity and the line at infinity. Great. And we also could see some kind of the duality, some relationship with the point and the lines. So when we also represent the line with some kind of the parameters like this, when we basically ABC stands for the parameters for the line equation like this, then we could now define the line joining the 2 points by taking the cross product of the homogeneous coordinates here, right? So it's basically the things that we are sort of like having the homogeneous coordinates both for the points and the lines. Then what we can do is that the good thing is that the line joining the 2 points can be obtained by taking the cross product, and also the intersection point of the 2 lines also could be calculated by the same cross product. So this was kind of the point and the line infinity that we have seen last time, right? And also what we have seen last time is that taking the cross product of the vector here, especially for the three-dimensional vector here, is that we can basically do the same calculation by defining the skew symmetric matrix in this way. So for the 2D, the point, which is represented with the three-dimensional vector with the homogeneous coordinate, if we define the skew symmetric matrix like in this way, then now this cross product can be represented as kind of the matrix vector the multiplication. So this is also what we have seen, right? So this is called the skew symmetric matrix because you can say that the elements in the matrix are kind of like symmetric, except for that the signs are basically different for the symmetric the elements like this, right? And also speaking to this skew symmetric matrix for the three-dimensional vector, one quick question is that what is the determinant of the 3 by 3 the skew symmetric matrix? So when you see this kind of like specific matrix here, what's the determinant of this? Can you see this? Yeah. So you can say that actually if you calculate the determinant yourself, then you can say that the determinant of the 3 by 3 the skew symmetric matrix becomes 0. So the effect that we are going to use in the rest of the lecture is that actually the three skew symmetric matrix is not a full length matrix. And so this basically means that the rank of this like 3 by 3 matrix becomes not 3 but 2. Okay. So this is kind of the effect that we are going to use in the next part of the lecture. Any questions on this? So please keep this in mind because we are going to get back to this later. Also, what we discussed last time is about the camera resectioning. So now we can see like how we can define the camera matrix. Then here the question is that how we can calculate the camera matrix from some kind of given information. So the first thing that we are going to see is that basically given some kind of the 2D to 3D correspondence. So when you know some kind of some points in the 3D space, and there's some kind of the coordinates, 3D coordinates in the 3D space, and when you also know that where these 3D points are projected over the image plane, then how can you basically calculate the camera matrix P here based on the bunch of the 2D to 3D correspondence here? So this is also what we have briefly seen last time, but if we get into some kind of deeper into some more the details there, what we can say is that actually there's some kind of scale ambiguity for the camera matrix P here. Because like what we know is that whatever the scalars and non-zero scalar that we multiply into the matrix P, it does not basically change the correspondence, right? Because like everything is now represented with the homogeneous coordinate. So whatever the non-zero scalar that we multiply to the 2D coordinates, the 2D homogeneous coordinates and the 3D homogeneous coordinate, it does not change the meaning of their position, right? So which means that we can also multiply any scalar to this like the camera matrix. So which means that there are some kind of the scale ambiguity. So which we cannot determine the scale of the matrix. So which means that when you basically find the camera matrix P here and multiply this into the 3D coordinates here, the homogeneous coordinates of the 3D point here, it may not be exactly the same with the 2D, the homogeneous coordinate of the 2D point that we have. There might be some kind of a scale difference, right? And this scale difference can be also different depending on the correspondence that we have. So which means that either we need to basically also jointly calculate the scaling factor for each of the correspondence, or without basically having the scaling factor, we should be able to calculate the matrix P here. So that's kind of thing. So which means that we cannot basically solve this problem, like finding this P here, basically making some kind of linear system, which is making the P times the capital X, this become the same with the small x here, because there will be some kind of scaling, some kind of the difference. So instead of like solving that linear system, what we are basically seeing is that while there might be some kind of scale difference between these two, what we know is that these two vectors should have the same the direction, right? May not have the same the magnitude, but should be basically the parallel. So based on that, what we are going to do is that we are going to use the fact that the cross product of like these two should be 0, right? So we are now solving this equation. Basically, given the xi and the small xi and the capital Xi, we are basically finding the p here. So that's the problem that we are going to find, right? Then how we can basically solve this? For that, basically, what we are going to see is that, yeah. So basically, we are going to represent the matrix P here with the 3 rows. What we know is that this like matrix P is the 3 by 4 matrix, right? And the small x and the capital X, these two are basically the given information. So let's say this like P1, P2, P3 basically represent each of the row. So it's basically the transpose of the row of each of the camera matrix here. So having the P1 and P2 and the P3. So these are basically the variables that we are going to optimize, right? And based on that, like if we calculate the cross product of like these two, that as we have seen in the previous slide, it becomes like identical to multiply the skew symmetric matrix right here. So basically, you can say that this is the equation for the only one, the single correspondence, for the one single correspondence, right? So for the single correspondence, like we are basically now having this kind of the equation. And based on that, like we want to calculate this like P1, P2, and P3 that satisfies like this multiplication to be 0, right? Clear? It's kind of like tricky in terms of that, like this P1, P2, P3. These are basically, basically the combined with the xi here, multiplied with the xi here. So that basically makes like tricky to basically find the P1 and P2 and P3. So basically what we are going to do is that we are going to rewrite the same equation in different way. So what we can see in this equation is that we are taking some kind of the dot product of the P1 and the Xi, and the P2 and the Xi, and the P3 and the Xi. So taking the dot product here first, and taking the multiplication between these two matrices, right? And now we can see that, so this is kind of the multiplication of the 3 by 3 matrix and 3 by 1 vector. We're gonna rewrite, because basically what we want to do is that we are going to make this, the multiplication to be zero vector, right? So making all this like multiplication to be zero. And we are going to rewrite this into this form. Now we are not taking the dot product on the right-hand side only here, but basically multiplying the scaling factor first to the xi here, and then taking the matrix of like these two, the matrix and the vector in a way that becomes the same with the taking the dot product here. So let me switch to the laser. Yeah. So instead of like taking the dot product here, now we are multiplying this scaling factor to the xi first, and then like multiplying this matrix, whole matrix, and this vector becomes the same as basically taking the dot product here and also taking the sum, right? So you can see that actually, while we are having some different dimension of the matrix here, the output should be the same. The output should be basically the same as the three-dimensional vector, and it should be also the same as the zero vector, right? Is this clear? So, but the difference is that instead of like having the 3 by 3 matrix and the 3 by the 1 vector here, now we are having the 3 by 12 the matrix and the 12 by 1 the vector. Basically, kind of like expanding the dimension of the matrix while the output should be identical, right? It is clear? Any questions on this? Then what's the kind of the benefit of like having this kind of like different sort of the the forms of the matrix demultiplication? The good thing of like this is that now we can decompose like all the things in a way that we are having like one matrix which can be computed based on all the information that we have. We basically the xi is the 3D points, and here all the small xi, yi, and the wi, these are basically the homogeneous coordinates of the 2D point. So these are all the given information. So we can calculate the matrix on the left-hand side, while the vector on the right-hand side becomes the variable that we want to calculate, right? So we can basically decomposing this kind of the matrix multiplication in a way that we are basically having like one matrix that can be calculated from the given information and having the vector, which is representing our the variable. So now what we can see is that now we are obtaining the homogeneous like linear system, which has the form of the m times the p equals 0, right? So we are having the like one matrix, and this becomes the variable. So it becomes the form of the like a times x equals 0, right? So this is the homogeneous the linear system with our the 12-dimensional the vector, 12-dimensional the variable that we have, right? But so it sounds like we're having the three equation for the 12 the parameters. But the thing is that one of those equation is actually linearly dependent on the others. So you can see that the third equation here, so if we go back to the previous slide, the third equation, third row here, actually can be represented as the linear combination of the two rows. And also the other row is the same, which means that one of those like three equations is basically useless. We just need to take the two equations. So now we can see that actually from like one pair of the 2D and the 3D the points, we can obtain like two equations, two homogeneous like linear equation, while we are having the 12 parameters. Does it make sense? So what just we need to do is that, so we are having like, given from the one point correspondence, we are having like two homogeneous like linear equation. And then given from the n number of the point pairs, we can accumulate these kind of like linear equations in terms of that we are making this like the homogeneous linear system with the 2n number of the equations. Just like, basically accumulating all the rows of the left-hand side in terms of like making a like one big linear system. And given this kind of like linear system, what we want to do is basically finding basically the non-zero solution, right? So this is like what we need to do. So then the problem becomes like simple. Basically, how we can find a non-zero solution given the homogeneous like linear system. So based on that, what we are going to see is that there can be basically multiple ways that we can obtain the non-zero solution. We can use either the Gauss-Jordan elimination, or we can use the SVD. But here the question is that actually the degree of the freedom of the matrix P is not 12, but 11. So can you guess like why is the degree of the freedom of the P is not 12, but 11? So we are losing 1 degree of the freedom. Yeah, because of the scale ambiguity. So when we basically have some kind of the non-zero elements in the matrix, basically what we can do is that we can basically, like, for example, like fix one of the non-zero element in the matrix to be 1, while basically determining basically scaling the matrix and determining the other elements based on the number of the one of the elements, the non-zero element, which means that while we are basically having the 12, the number of the parameters there are only 11 things to be determined. So that means that actually the degree of freedom is 11, not 12. So which means that if we have the linearly independent 11D equations, then based on that, we will be able to basically determine this kind of the unique solution. But also here, the question is that in the overdetermined case, like when we basically have some more than some kind of the 11D equations, what is the condition for the matrix DM here in the matrix here? Here, this to be have some kind of the non-zero solution. Yeah, so there should be some rank deficiency, right? So the rank should not be 12 or greater than 12. So that's kind of thing. So when we basically know that when there exists a non-zero solution given this kind of the homogeneous linear system, basically what we can do is that we can simply use the SVD, as you may learn from the linear algebra course. So basically, once we decompose the matrix M into the two orthonormality matrices and the diagonal matrix here, then how can you find a vector P that satisfies like this the homogeneous linear system? Basically, this vector P becomes the vector in the V here, the row here, which is corresponding to the smallest the singular value. So what we can see is that if we take the vector of the V here, which is corresponding the smallest the singular value here, which is now 0. So if the matrix is not the full length matrix, then we're gonna see that actually the singular value will be 0, right? Then basically what we can say is that when you take the last the column of the V here, and so it becomes like we are taking the product like this whole decomposition with the Vn here, right? And since the V is the orthonormality matrix, like the first n-1 the element will become 0. Because like when you take the dot product with the Vn with all the other basically the vectors here, by definition of the orthonormality matrix, like all basically the dot product will become 0, and only the last one will become 1, right? And since like the first n-1 the elements become 0, whatever kind of the numbers that we have for the diagonal the part here, which also becomes 0 because of the right-hand side is because 0. So only the last one becomes the non-zero value, but the thing is that now the singular value corresponding to that is also 0, right? So we can say that when you take the Vn as some kind of the vector here, when the corresponding the singular value of the Vn is basically 0, then we can say that this vector becomes the solution that we are finding, the non-zero the solution, basically satisfying the of that basically the homogeneous linear system. So this is kind of like simple way that we can basically solve the homogeneous linear system. So decomposing the given the matrix M using the SVD and taking the singular vector with the corresponding to the zero singular value in the right hand side in the V matrix here. It is clear. And this is the case like when there exists the non-zero solution for the given the matrix. But this is kind of some kind of special case that there is basically no kind of any kind of the noise in the given the point correspondence. So if we have some kind of the perfect set of the 2D to 3D correspondence, we will be able to find some kind of the solution, the non-zero solution satisfying that. But if we start to have some kind of the noise in the given the 2D and the 3D coordinates, then we might, and we also have some kind of the bunch of the pairs of the points, making some kind of the over-determined the case, then we're gonna see some kind of the cases that the M becomes the full length, and there is basically no non-zero solution satisfying this linear system. So in this case, like we can consider basically finding the best solution, which is basically minimize some kind of the errors in the point correspondence. And for that, actually, there are kind of a bunch of the ideas for that. The simplest way to find the best solution is to find the vector P, which is like minimizing this norm. So this norm is called the algebraic error, which is not exactly the same with some geometric error, some kind of the distance either in the 2D or the 3D space, but this is kind of some kind of the simple way that we can find some kind of define some kind of a good solution. And the good thing of like defining this like the algebraic error is that the way that we are finding this kind of the vector P, minimizing this error, is the same as we find some kind of the non-zero solution in the case that when the non-zero solution exists, which is the case that we are finding the rightmost the vector of the V here, which is corresponding to the smallest the singular value. So either when we have some kind of either when there exists a non-zero solution or not, if we take the rightmost the vector in the V matrix here, which is corresponding to the smallest the singular value here, then if there exists a non-zero solution, then the smallest singular value will become 0. And then the Vn here, the rightmost vector, will become the non-zero solution. In the case that when the non-zero solution does not exist, if we still take the rightmost vector in the Vn here, which is corresponding to the smallest the singular value, that will be basically the case that we are finding the camera model, which is minimizing the algebraic error. So that's basically the things that we can do with the SVD. But obviously, there are some kind of more sophisticated way that we can really minimize some kind of the distance either in the 2D or the 3D space based on kind of the given the correspondences. But I just like to tell you that this is kind of the simplest way that we can find some kind of good solution, even in the case when there are some kind of the noise in the 2D and the 3D coordinates. Okay, any questions on this? But so this was basically the case that we are finding the camera model in case like when you know the 2D to 3D the correspondence. So literally like in the world coordinate system, we know the 3D point and they're the coordinates, right? And we also know they're the projection in the image plane and they're the coordinates in the 2D the image in the space. So in such kind of case, we can use this idea to calculate the camera model. But for many of the cases, it would be really challenging to really measure the 3D coordinates in the 3D space, and also there the projection, finding there some kind of corresponding the point in the 2D image and getting some kind of the 2D coordinates. So it may not be that practical way to really calculate the camera model. While we can do is that actually finding the 2D to 2D correspondence is much easier the task, like when you have the multi-view images. So basically what you can do is that when you really know the 2D to 3D the correspondence, we can use this idea to calculate the camera model. But typically that's not that practical. So for many of the cases, it becomes much easier to find the 2D to 2D correspondence for the different view images. And what we are going to discuss in the rest of the part is that given this kind of the 2D to 2D correspondence, how we can also calculate the camera pose. So that's also kind of the things that we are going to in the next step. But before we move on to the next step, any questions on this? Okay. So you can see that basically what we are doing here is that given some kind of some point-wise correspondence information, how we are going to obtain the camera model. And once we have the camera model, then we can calculate the projection from the 3D to 2D, and we can also see some kind of the relationship between these two, right? So basically, especially in the case that when you have a set of the multi-view images, how we can do some kind of the like get all the 3D the camera pose information and do some kind of the 3D construction based on that is kind of some kind of the technique which is called the structure from motion, which is really kind of the very complicated framework, which is involving many of the parts in the whole framework. And this is really kind of the big topic that we can actually discuss over the entire semester. So we are not gonna get into too much details for all the things. We're gonna skim through some kind of the basic ideas in terms of like how we can really get some kind of get some kind of camera pose information and also do some kind of the 3D construction. And if you are interested more into some kind of more details, I'd like to recommend you to check out this like the CoolMap library, which is like some kind of the de facto, some standard kind of library for the structure from motion. And you can also check out many details in terms of how we can really implement this kind of like full framework, basically getting from the 2D, the multi-view images, and how we can get some kind of 3D the concept of the outputs. But if we basically very briefly see some kind of the basic idea, basically what we are doing for each of the component in the framework is that first, like given a set of the 2D multi-view images, what we do is that we, as I mentioned in the previous slide, we find some kind of the 2D to 2D point correspondence first. So that's kind of the basic building block in terms of calculating all the things. So finding some kind of the 2D pixel-wise like correspondence across the images. And for that, actually, we can discuss lots of some kind of techniques in terms of how we can really find some kind of 2D correspondence. There are also lots of the techniques. This is really the subject that has been studied more than 2 decades. It's really kind of like the basically big topic. And there has been very classical ideas in terms of like how we can extract some kind of the key points in the 2D images like this, and also how we can define some kind of the feature vector for each of the key point in a way that we can basically find the correspondence based on by comparing the feature. So I don't know like how many of you know the name of the shift and the surf. These are some kind of the very famous technique in terms of like finding those kind of correspondence, which has been like introduced like more or less like 20 years ago. Obviously, like these days, people don't use these kind of some classical ideas. People also use the neural net to basically define some features for each of the points. So there are some kind of the many learned features in terms of like finding some kind of the correspondence across the images, the multi-view images. And based on that, basically what we are going to do is that so basically we are going to first assume that the camera intrinsic matrix is given. So there is also kind of another line of the technique that we can actually also calculate the camera intrinsic matrix, or the camera intrinsic matrix is basically some intrinsic parameters which can be actually provided by the manufacturer from the camera manufacturer. So for each of the camera, actually there's some kind of the known the intrinsic parameters. For example, if you're using the iPhone, for the iPhone the camera, for each of the model, there is some kind of the known the intrinsic parameters, while it can be slightly different depending on the exact hardware, the device, the phone that you have, right? So when you basically assume that the camera, the intrinsic parameters are kind of the given, what we need to basically calculate is basically is the camera extrinsic parameters, right? The rotation and the translation. And this rotation and the translation would be also dependent based on how we define the world coordinate system, right? So we can define the world coordinate system as we want. And the typical idea for that also would be basically we set the camera coordinates of the first image as the world coordinate system. And all the relative, some kind of the camera pose from the other, the images are basically defined based on the camera coordinates of the first image, right? So this is kind of like the typical simple way that the camera coordinates of the first image becomes the world coordinates, and then all the relative the camera the coordinates for the other images becomes the camera the coordinates for each of the images, right? And then the question is basically how are we gonna calculate the camera the extrinsic parameters for the other images, right? And so we're gonna get into that basically how we can calculate the camera the extrinsic parameters for some other images. And based on that, what we do is that for the given the 2D, the corresponding the points for each of the images, now what we can do is that we can shoot the rays for each of the camera and see the intersection point in the 3D space. So if everything is like perfect, if the correspondence is perfect, and also the camera pose, the extrinsic, intrinsic, the parameters are very accurate, then these two rays should meet at the one intersection point. While as we have some kind of the noise for all the correspondence and the camera, the parameters, there might be some cases that the rays are not really intersecting in the 3D space. But basically, if everything is basically perfect, then we will be able to see some kind of the corresponding 3D point from the 2D correspondence. But since there might be some kind of the noise and the errors in our calculation, we might also want to run some kind of the optimization, basically optimizing everything, all the correspondence and the camera parameters with some kind of the sophisticated, some kind of optimization scheme. So these are some kind of the components in the structure from motion. For every step, actually, there are quite many things that we can discuss while we are not going to discuss like any kind of details there. And also there are many some kind of the tricks that we can use in terms of like improving some kind of the accuracy for the many things. For example, we can consider using the rank set to find the inlier set of the corresponding points. How many of you are familiar with the rank set idea? Maybe if you took the computer vision course or something. So yeah, so I'm not also gonna get into any details for the rank set, but this is also kind of the technique in terms of like finding some kind of the inlier the set of the corresponding points. So basically, when you have this kind of the pointwise the pairs across the different images, there might be some kind of the noisy correspondence like this, right? Then what we can do is that we're gonna actually see how we can represent this kind of the pointwise correspondence across the 2D images into the matrix form. So actually we're gonna see this kind of the matrix form. And if we find some kind of the correspondence which is not really fitted with some kind of the model that we have here, then we can basically take out them as kind of the outliers. By doing this kind of filtering, we can also improve some kind of quality of the camera models that we're calculating. And also in terms of like doing some kind of the global optimization for the everything, before we do run the optimization for the every like correspondence and also the camera models as well, only for the rotation part, for example, for the across the relative camera pose, we can also do some kind of the optimization. So especially the case that we are doing some kind of the optimization only for the 3D rotation, it's called the rotation synchronization or rotation de-averaging. Here the basic idea is that if we have the relative the rotation from the image 1 to 2 and 2 to 3 and 3 to 1. So let's say we have some kind of the relative, some kind of rotation from the image 1 to 2, 2 to 3, and 3 to 1, right? So if you multiply these three, then when you get back to the first image, the rotation should be identity the matrix, right? So these are some kind of the constraints that we have for the camera pose that we are going to calculate. So using this kind of some kind of constraints, we can do some kind of the more sophisticated kind of the optimization to further improve all the accuracy for everything. While we are not going to get into any details here, but what I'm just telling you is that there are actually lots of some kind of details that we can basically involve in the framework in terms of like improving the accuracy. So as I said, like this is really kind of the big topic. Every component we can discuss like many things. The things that we are going to discuss for today is basically like one small part. Like given the 2D correspondence across the multi-view, the different view images, and also when you assume that the camera intrinsic matrix is kind of given, how we can calculate the extrinsic parameters, the relative camera pose across the images. So this is kind of like the basic, the building block in the pipeline of the structure promotion. So for that, we are going to talk briefly, very briefly talk about the epipolar geometry. But before I move on to this, any questions on this? And by the way, if you are interested more about some kind of the details here, I'd like to recommend you to check out this textbook, the Multi-View Geometry in Computer Vision, which is basically summarizing all the ideas about the structure promotion with some kind of very deep kind of the theories as well. And we're gonna basically skim through some kind of basic ideas here. So to talk about basically how we can calculate the relative camera pose from the 2D correspondence, I'm going to introduce some kind of the new terms. So please follow me in the next of these slides. So there are some of the terms here. So let's think about that. We know some kind of the 2D point correspondence. So we are having the first image here and the second image here. So let's say like the X is the point over the image plane of the first image. And depending on, which means that there will be a 3D point which is projected into this point, right? So given the 2D point X here, there will be a 3D point on this line, on this ray, which is projected into this point. So given the 2D point, actually, we don't know exactly the position of the 3D point because it can be any of the point over this ray, right? So when you shoot a ray from the origin of the camera here to the image, the point here, then any point over this line can be the corresponding 3D point. Make sense? And when you also project this ray onto the second image, which means that this line will be projected onto the line as well in the second image like this, right? And which means that any point over this line can be the corresponding point with this point, right? So even in the case that we don't know what's the kind of the corresponding point of the X in the first image, in the point in the second image, it doesn't need to be, it's not the case that any arbitrary point in the second image can be a corresponding point of the X here. Only the point over this line can be a corresponding point of the X here, right? So this line, where the corresponding point of the X can be present, will be called the epipolar line of the X. So given any point X here in the first image, when you talk about the epipolar line in the second image, we see basically the line where the corresponding point of the X can be placed. Make sense? So when you have the X here, no, we're gonna define the L, let's say X prime is basically the corresponding the point, and the L prime is basically the epipolar line. Which means that this X prime should be on this like L prime, right? So which means that the dot product between these two should be 0, right? Make sense? Then let's think about the epipolar line for the arbitrary point. Not only having the X here, for the other point here and here, for the first image, let's say like we shoot a ray into the 3D space and projecting them into the second image, right? Then we're gonna see some bunch of the epipolar lines in the second image, right? The thing is that actually all the epipolar lines in the second image will have the one intersection point. What's the intersection point? Can you guess? For any arbitrary point in the first image, if we basically shoot a ray in the 3D space and project them into the the second image, there will be, for all the epipolar lines, there will be one single, the intersection point for all the epipolar lines. Actually, that intersection point may not be inside the image, but outside of the image, but in the infinite plane, right? Actually, what we can say is that all the rays that we are shooting in the 3D space is starting from the origin here, which means that all the 3D lines that we are also drawing in the 3D space will also have the intersection point at the origin. So which means that like all the epipolar lines will be also intersecting at the one point, which becomes the projection of the origin of the first the camera of the first image. So if we basically project the origin here, the first the camera the origin of the first the camera to the second image here, that becomes the point where all the intersection, all the epipolar lines basically passes through. Does it make sense? So in terms of that, we can define the epipole, which is now basically the intersection of basically the camera center of the first image to the image plane of the second image. And this is basically the point where all the epipolar lines basically passes through. So in this way, now we are defining the epipolar lines, which is defined for the one of the point in the other image, and the epipole, which becomes the intersection point for all the epipolar lines, right? Is this clear? This is kind of the concept that we are going to use for the rest of the slides. Okay. Any questions on this? Condition for the planes are not inclusive, right? I couldn't get the conditions for the planes. What do you mean by conditions for the planes? So yeah, let me first move on. So based on, well, I mean, the planes are basically the image plane. So as I said, like as we discussed in the previous slide, we can basically set the image plane based on the focal length that we define, right? So if we have some kind of the default camera, the plane will be basically the plane where the z becomes 1 in the camera coordinate system. So based on this kind of the definition of the epipolar lines and the epipole the point, what we are also going to define is the fundamental D matrix. So what we are going to do is that the relationship between the corresponding points in the first image and the second image will be represented with a 3x3 rank 2 matrix. So let's forget about the rank for now. So we are basically having a sort of the 3x3 matrix, which is basically defined in this way for the to the corresponding points represented with the homogeneous coordinates. We're gonna basically find a matrix F here, which satisfies this. So let's say like X is the 2D points in the first image, and the X prime is the points in the second image. Then we're gonna basically see that actually the correspondence can be represented with the 3x3 matrix F here. Okay. So this is the definition of the fundamental D matrix. Actually, what we can see is that this fundamental D matrix is mapping, is basically also representing the correspondence of like these 2 points. Actually, what we can see is that by definition of the fundamental D matrix, this matrix is actually mapping the point in the first image into the epipolar line in the second image, because of the fact that the dot product of these two should be 0, right? So when you combine the definition like this and the line representation here, we can see that actually this matrix F is now mapping the 1 point in the first image into the corresponding the epipolar line in the second image. So you can see that F is the mapping function from the point to the epipolar line in the other image. Okay, makes sense? Now here the question is that, so this is the matrix like mapping the point in the first image to the epipolar line in the second image. How about the opposite? So given that the F is the fundamental matrix from the image like one to the other, what's the fundamental matrix from the second one to the first one? So the fundamental matrix for the other way around should be basically mapping the point in the second image to the epipolar line in the first image, right? What is such kind of the matrix? Yeah, actually it becomes the transpose. So if you transpose the matrix F, you can see that actually that is mapping the point in the second image to the epipolar line in the first image, right? So what we also, is this clear? Any questions on this? So now we are basically seeing that by definition of the epipolar lines and also the fundamental matrix, we can see how they are basically related to each other, right? And also the thing is that what's the relationship between the epipole and also the fundamental matrix? So what we have seen is that for any kind of let's say the x is the point in the first image, and the L prime is the corresponding the epipolar line in the second image, right? And we know that basically the epipolar line, any epipolar line in the second image should pass through the epipole. So which means that the dot product of the epipole and also the line, the parameters for any epipolar line, these two should be zero, right? So whatever x we have, whatever point in the first image that we have, if we find its corresponding the epipolar line, the dot product between these two should be zero. Which means that whatever the x we have here, this should be zero, which means that now the product, the multiplication of like the first two should be zero, regardless of the choice of the x here. Make sense? So what you can see is that when the E prime here, this is the epipole in the second image, the product of the E prime, the epipole, and the fundamental matrix, these should be zero. So what we just need to do in terms of like finding the epipole is that given the fundamental matrix, if we find a vector which the left side multiplication to the F matrix here becomes zero, that's the epipole in the second image, which we call the left null vector of the F. And similarly, by definition, we can also say that the null vector of the F also becomes the epipole in this first image. So now we can see some kind of the relationship across the epipolar line, epipole, and the fundamental matrix, right? Any questions on this? So I recommend you to check this out in terms of like how these are basically defined, and based on those definitions, how we can also derive like this, right? So yeah, moving on. So this is all about like epipolar lines and epipole and the fundamental matrix. And one thing that we are also going to define is the essential matrix. So essential matrix is basically nothing, but we are basically discussing everything here, not with the arbitrary image coordinates, but with the default camera, with the normalized to the coordinates. So this is basically the kind of the things that we are taking out the factor of the intrinsic matrix. So when you basically multiply the inverse of the intrinsic matrix to the image coordinates, then we are getting the normalized to the coordinates, right? So this now becomes that we are talking about the same thing, but while taking out the factor of the image, the intrinsic coordinates, the parameters of the camera. Then the essential matrix is basically the same with the fundamental matrix, but the only difference is that now we are defining the same thing for the not the image coordinates for the with some kind of arbitrary the camera the intrinsic parameters, but for the normalized the 2D coordinates, right? The same thing, right? So we are just changing the term. And also basically typically what we assume is that actually depending on the situation, the camera intrinsic parameters from different images can be also different, right? So it can be the case that we are taking the photos from different position also with a different camera. But to simplify the discussion here, because we're going to assume that we are using the same camera to take all the photos, which means that we are sharing the camera intrinsic parameters across all the images. Right? So in any case, like when you talk about the normalized 2D coordinates, similarly with the fundamental matrix, we can also see that these are basically representing also the normal epipolar lines of the normalized coordinates, right? And then by definition of that, now we are replacing, the image coordinate here with some kind of by multiplying the inverse of the intrinsic matrix here, we can see this kind of relationship between the essential matrix and the fundamental matrix. So which means that if we know the essential matrix and also the camera intrinsic parameter, based on that, we can calculate the fundamental matrix. Or the other way around, like given the fundamental matrix, if we know the intrinsic matrix, based on that, we can also calculate the intrinsic matrix. So there are basically a bunch of things we are discussing, like epipolar lines, like epipole, like fundamental matrix, and the essentiality matrix. And we're gonna see like why we are basically introducing like those things. So the thing is that given some kind of the 2D coordinates, so we are assuming that the 2D correspondence is basically given, and also the camera intrinsic parameters are given. So based on that, what we are going to see is that we can see how we can calculate the fundamental matrix. So once we basically calculate the fundamental matrix, based on that, now we can calculate the essential matrix. And the essential matrix, we're gonna say that actually the essential matrix is basically having some relationship with the extrinsic parameters that we are also going to calculate. So that's basically the reason why we are basically discussing this kind of bunch of the concepts. Any questions on this? So here the thing is that how is the essential matrix related to the extrinsic parameters? So let's see this. So like this is kind of the setup that, as I said, like we are setting the camera coordinates of the first image as kind of the world coordinates. So in terms of that, now the rotation and the translation with respect to the world coordinates becomes like identity and the zero translation, which means that the camera coordinates of the first image and the world coordinates are basically the same. It depends on like how we define the world coordinate system, but let's simplify in this way, like we are defining the camera coordinates of the first image as the world coordinates. And then, based on that, taking the camera coordinates of the first image, the world coordinates, we will define also the extrinsic parameters for the second image with the rotation here and the translation. So this is basically the extrinsic parameters for the second image. And then this like E hat and the E hat D prime, these are basically representing the epipoles in the normalized coordinate system. So we are not introducing kind of the camera intrinsic part here. Clear? So based on that, basically what we can see is that we have seen that the epipole in the second image was the projection of the origin of the first the camera, right? Now the camera coordinates of the first image is the same with the world coordinates. So what you can see is that actually epipole becomes the projection of the origin of the world coordinate system into the second image, right? So this is the thing, like the origin of the world coordinate system, projecting this into the normalized coordinate system in the second image, multiplying the extrinsic parameters. These should be the same with the epipole here. Make sense? So from this, what we can see is that the translation parts of the second image should be the same with the epipole of the second image. Make sense? So now we can calculate the epipole of the second image. Not calculating, but this is basically the same with the translation here. So this is like the one fact. And the second thing is that if we see the epipolar line, from the one of the point in the first image to the second image, so what we can see is that basically the point that we are basically projecting can be calculated in this way, right? Given any point here, if we basically calculate the projection into the second image, that will become the multiplying the extrinsic parameters here. And also the epipolar line in the second image should basically pass through the both of the projection point of like this, and also the epipole here, right? So which means that, so actually there are two ways to representing the epipolar lines for any of the point in the first image. So basically the epipolar line of the one of the point here can be represented by just multiplying the essential D matrix, or basically taking the cross product of the epipole and also the projection of the point. So these two should be the same, right? So either we have the essential D matrix here, or basically having some kind of the taking the cross product of between these two should be the same. So by basically deriving all the kind of details, actually what we can see is that actually the essential matrix is having this kind of form, taking the cross product, no, not cross product, it's taking actually the skew symmetric D matrix here, multiplying this by the rotation matrix here. So this basically shows some kind of the relationship between the rotation translation that we are going to calculate and the essential D matrix. So what we are actually going to see is that once we can calculate the essential D matrix here, based on this, actually we will be able to derive the translation and the rotation. So this basically shows the relationship between the essential matrix and the camera pose that we are going to calculate. It is clear? So again, like we are basically having two ways to representing the epipolar lines here for any arbitrary point here, which can be just like multiplying the essential matrix to the point, or taking the projection of the point, which is basically multiplying the extrinsic parameters and taking the cross product of the epipole here, which is like by definition should be the line connecting these 2 points. And we know basically the epipole here is the same with the translation part here. And based on that, we can derive that actually the essential matrix can be represented with the multiplication of the skew symmetric matrix here, defined with translation and the rotation. Basically showing the relationship between the essential matrix and the camera matrix that we are going to calculate. It is clear? So I recommend you to check this out yourself and see how we exactly calculate this. And also one thing that we can see is that, so basically this matrix E also should have some scale ambiguity, right? Because like these are multiplied with the homogeneous coordinate. So basically whatever kind of the non-zero the value that we multiply to essential D matrix, it does not change the meaning, right? So there should be some kind of scale ambiguity. So that's basically the one thing. And the second thing is that now we can say that the matrix E is now represented as kind of the multiplication of the 3x3 skew matrix and the rotation D matrix. So this is kind of like important thing, because like when we talk about this 3x3, this skew symmetric D matrix, as we have seen in the previous slide, is the rank 2 matrix. It's not the full length D matrix. And actually the essential D matrix is represented as the multiplication with the skew symmetric D matrix, which means that the essential matrix is also not a full length D matrix. It's also the rank 2 matrix. And also it's the same for the fundamental matrix as well. So fundamental D matrix is also represented with the multiplication with the essential D matrix, which means that the fundamental matrix also should be rank 2 matrix. So all the fundamental matrix and the essential matrix, those two matrices are basically having the non-full length D matrix, rank 2 matrix. And also, as I said, they are also having the scale, the ambiguity. So whatever kind of non-zero value that we can multiply those kind of matrices. So this means that while we are basically having the 2 3x3 matrix, which are basically having the 9 elements, actually the degree of the freedom for each of the matrix will be 7, because we are having the two constraints. Like one is that there is like scale the ambiguity, and second thing is that also the rank should not be full length. It should be, the rank should be 2. So this means that actually we need to have the 7 equations to determine each of the fundamental matrix and the essential D matrix. It is clear? Any questions on this? So actually, there are more details. So what I'm going to talk about based on this is that so how we can really compute the camera the extrinsic the matrix. And the way for that is that we are now assuming that there are some kind of the 2D correspondence across the images, and also the intrinsic the matrix is given. So kind of the procedure that we are calculating the camera D matrix is that given the 2D correspondence, as we have seen in the camera D resection in the case, we are first going to calculate the fundamental D matrix given the 2D correspondence. And as we have seen, once we can compute the camera the fundamental D matrix, if the intrinsic D parameters are known, then based on that, now we can easily calculate the essential D matrix, right? And we have seen that the essential D matrix is represented with some multiplication of the translation and the rotation. And we're going to see how we can decompose the essential matrix into the translation part and the rotation part. Then now we are getting some kind of the relative, the camera, the extrinsic the parameters, the camera, the pose, given for the second image, given the first image. The procedure is that, as I said, like we are having the pixel-wise correspondence first. Based on that, we calculate the fundamental D matrix and multiplying the intrinsic the parameters in terms of getting the essential D matrix. And given the essential matrix, we decompose this into the translation and the rotation in a way that we finally get the camera the extrinsic D parameters. So this is kind of the procedure that we are going to try. So next time, I'm going to get into slightly more kind of the details in terms of how we can exactly do this kind of calculation. And as you can guess, actually, this kind of computation will involve some kind of the bunch of things about the linear algebra. While we are not going to have some time to discuss all the details. So the slides are already on the website and also in the link, and I'd like to recommend you to check out some details there. And then after discussing all the things, we're gonna move on to the neural rendering and see how this kind of the estimated camera parameters can be also used for more like find some 3D reconstruction. Okay. Any questions on this? So let's continue discussing the epipolar geometry next time, and we're gonna move on to the neural rendering. Okay. Thank you. Bye.